right, welcome back. So we continue with the second part of this chapter 2 with a focus on chapter 2.3, the conditional expectation. But first we finish the discussion we ended up in the last lecture. So we talked about the covariance and defined the covariance like it is written down here, right? And clearly when x and y, random variables x and y are independent, then the covariance is equal to 0. And then we say that x and y are uncorrelated. And the converse need not be true. And we will show an example in a minute of this fact. Yeah, and finally we also defined the correlation coefficients rho of x and y being the covariance of x and y divided by the standard deviation of x times the standard deviation of y, and that correlation coefficient lies between -1 and 1. Perfect correlation being 1 and perfect negative correlation being rho equals -1. Now, we have seen that in the case of one random variable, the expectation of a function g of x is defined as the integral of g of x of little omega dp omega. And this can be written with the distribution measure as the integral of gx d mu x. Now, similarly, we have it in the multidimensional case. So the expectation of a function of g of x and y, that is then defined similarly. So it is the integral of g of x little omega, y little omega, dp omega. And that can be defined with the joint distribution measure mu xy, so it is the double integral, the integral over R2 of gxy d mu xy, provided of course that this expected value of the absolute value of g of x and y is finite, it's provided it exists. Now when x and y are independent, then we have this this notion from the previous hour that the joint distribution measure can be written as a product of the marginal distribution measures of x and y. And this expectation of g of x and y is then defined similarly with the double integral, the integral over r square of g of x and y, and then here we encounter the marginal distribution measures d mu x, d mu y. Now let's look at an example. So again, we go back to this, the converse need not be true in on this slide. So let's look at an example of uncorrelated dependent normal random variables. And the example is defined as follows. Let x be a standard normal. So then x has a density, and fx is 1 over the square root of 2 pi e to the power -1/2 x squared. And let z be a discrete random variable with two possible states, the state z equals 1 and z equals -1, and they are both equally likely to occur. So the probability of z equals 1 is equal to the probability of z equals -1 is equal to 1/2. And now let's define another random variable, y, capital Y, and that is defined as x times z. And in more detail, this is defined as x if z is equal to 1, and it is -x when z is equal to -1. Now let's look at the distribution function of y. The distribution function of y at point B is defined of course, as the probability that capital Y is less or equal to B. And in our particular case with the two possibilities, Z equals 1 and Z equals -1, we can write this out as the probability that Y is less or equal to B when Z is equal to 1 and Z equal 1, plus the probability that Y is less or equal to B and Z is equal to -1. And writing this out in terms of X, we move from Y to X. So we look at this in more detail, and then we see that this is equal to the probability that X is less or equal to B and Z is equal to 1, plus that second part is different. It's the probability that minus X is less or equal to B and Z is equal to -1. Because from the definition, Y is composed, can be written as follows. It's X times the indicator function that Z is equal to 1 minus the X times the indicator that Z is equal to -1. So these two events are independent. The Z equal 1 and -1 is independent from X. So we write this even further, this expression over here, and we can write it as the probability that X is less or equal to B times the probability that Z is equal to 1, plus the probability that minus X is less or equal to B times the probability that Z is equal to -1. And we had equal probabilities for these two. So the probability that Z is equal to 1 is 1/2, and the probability that Z is equal to -1 is 1/2, as you see it over here. So this ends up with, and the probability that X is less or equal to B. Well, we have a standard normal random variable, so that is typically denoted by N. Which is a little confusing because I think I used psi earlier on. Sorry for that. So it's 1/2 N of B plus 1/2 N of B, because again, so here we have essentially the same. Let me see. I have it written down here. I have this essentially the same because minus X is also standard normal. So therefore, we end up with the same term here, and in total, the distribution function of Y is equal to the distribution function of the standard normal. All right. Then we look further, and we see that, of course, this means, so with X being defined like this and Y being defined like this, this means that the expected value of X is equal to the expected value of Y is equal to 0. And also we have that the expected value of Z is equal to 0. Check that yourself. Now, if we look at the expected value of X times Y, and we rewrite Y as X times Z as it is defined, so this is the expected value of X squared times Z. And as these two are independent, Z and X are independent, this is then the expected value of X squared, the second moment of X, in fact, times the expected value of Z. And that is equal to 0. And this part forms a part of the covariance between X and Y, if you look at the definition. So the covariance of X and Y is equal to 0. However, X and Y cannot be independent, because if they were, then X absolute and Y absolute would be independent, but X absolute is equal to Y absolute. So this would lead to a contradiction. So here we have a counterexample. So two variables that are not independent, but the covariance being equal to 0. Okay. Then 2.2 in the book concludes with the definition 2.2.11. That is the definition of the joint normal distribution. So X and Y, they have a jointly normal distribution if the joint density function of X and Y is given as follows. So it is little f, the joint density little f of X and Y. It is defined as follows. It is 1 over 2 pi times sigma 1 times sigma 2, and sigma 1 being the standard, the volatility parameter, the uncertainty parameter of the first process. Sigma 2 of the second process times the square root of 1 minus rho squared, where rho is this correlation coefficient in absolute value less than 1. Otherwise, we would divide by 0, as you see, times the exponential of minus 1 divided by 2 over 1 minus rho square times x minus mu 1 divided by sigma 1 squared minus 2 times rho x minus mu 1 times y minus mu 2 divided by sigma 1 sigma 2 plus y minus mu 2 divided by sigma 2 squared. This is then the closed form expression of the joint density function. In this case, mu 1 and mu 2, they are the expected values, and sigma 1 and sigma 2, they are the standard deviations. This is the joint density, as we may often encounter it when we are dealing with multivariate normal distributions. All right, so let's discuss 2.3, section 2.3 in quite some detail. It is one of the more important parts here. It's quite fundamental in financial mathematics. We have seen a special case already in the first course of probability theory, but now we will do it in more detail. It's the heart of this course, if you wish. We will start simple to motivate the general definition. Yeah, so we start on a probability space, omega fp. We have the outcome space, the sigma algebra, and the set of all possible events. And it has the information structure as we discussed it in the first lecture. Plus we have a probability measure which is defined on F and gives every set in F a value between 0 and 1. And it should be sigma additive. And suppose we have a random variable with a finite expectation. Again, we start simple. We take an event A in F with positive probability. Note that we now have a natural way to divide our space. So we have our space omega, and we say our event A is over here, then naturally we divide our space into A and A complement, right? So A induces in a natural way a partition of omega, namely omega is A complement. Okay, going back to A, let's define a conditional expectation, like you used to do it before, of X given A. So what I'm saying is that the event of your experiment has property A. It lies in the set A. And given this fact, I would like to find out how I can define the average value of X. This is denoted by the expectation of x given A. And this is by definition the expectation of the indicator function of A. That your outcome is an element of A times x divided by the probability of A. Yeah, let's try to understand this equation. So to understand this a little bit better, we are going to view A as the probability space by itself. So I have to tell you what the sigma algebra is and what is the probability measure. So let me write it down like this. Consider the probability space, A, the outcome space, as I'm only interested in outcomes that lie in A. And on A, I take the sigma algebra F intersection A, right? As you see it over here. And I will take the so-called conditional probability measure. And I'll write it down with a subscript A, the conditional probability measure, with F intersection A being only looking at sets of the form B intersection A with B and F. And P of A is defined on F intersection A. So if I take any element in this sigma algebra, and I will explain what is the definition of PA of this set, it's nothing but the original probability of B intersection A divided by P of A, where division by P of A is just a normalization. Yeah, so we are here. Making the total probability of A under measure P to be equal to 1. That is the meaning of the normalization. If I consider this probability space, then what we wrote, namely the expectation of the indicator of A x divided by PA, is nothing but the average, the expectation of this random variable indicator A times x. This is a random variable defined on A with respect to the conditional probability measure P of A. So you're actually performing a regular expectation on a smaller probability space. Now what we are doing here, we are telling you that our outcome is in A, but of course, as I mentioned above, omega, our probability space, is partitioned into a disjoint union of A and A complement. So every time I have an outcome, it will lie either in A or in A complement. So if our outcome is in A complement, then we can perform the same procedure as we did here. So here you see our definition of the expected value of x given A, and we can do the same for A complement. So we can there also say it is the expected value, the expectation of x given A complement is the expectation of the indicator function of A times x, of A complement times x, divided by the probability of A complement. So similar to above, what you're doing here is taking a regular expectation under the conditional probability measure P restricted to A complement. Now, if we combine this information and we view the two possibilities in one function, we get the same, the following. So let's now define the sigma algebra of A and A complement, of course being the elements A complement, the zero set, and omega itself. And then we can write the expectation as follows. The expected value of x given this sigma algebra of A and A complement, that is defined as the indicator function of A, x lying in A, times the probability, times the conditional expectation of x given A, plus the indicator function of x in A complement times the conditional expectation of x given A complement. And we can substitute the definitions here, and that is, this is the definition of that conditional expectation, and this is the definition of the other conditional expectation. And this is an important notion. And remember that the indicator A and the indicator A complement, they are the random variables, and they are measurable with respect to that sigma algebra. The other two terms, this expectation here and this term here, they are in fact constants. Yeah. All right. Let's analyze another fact. So departing from this definition of the conditional expectation, let's multiply left and right hand side by an indicator function. Yeah. So see what happens. We multiply both sides by the indicator A. And I'd like to stress this, that this term is a constant. And this term is a constant, right? And the indicator functions are the random variables. Now, given this, let's take the expectation of the last product we wrote. So that is here. Let's take the expectation. So the expected value of this term over here, that's the left-hand side here, and the expected value of the right-hand side here, that is this term here. Now remember that this is in fact the where am I with my pointer here? That this term is in fact a constant, so I can take it out of the integration of the expectation operator. So this term gets to be here, right? We take it out of the expectation operator, and then what remains is the expected value of this indicator function. And in total, what we see here now is that this is nothing, but this is, of course, as you remember, this is the probability of A, and the probability of A cancels out then, right? We can cancel, they cancel out. And what remains is the conditional expectation of that indicator function of A times X. All right. So if we look at the left-hand side and the right-hand side, we have another important equality, another important property for conditional expectations. And in integral form, this looks as follows, right? The left-hand side here can be written as the integral over A. Think of the indicator function here, the integral over A times the conditional expectation of X given A dp. And the right-hand side here can be written as the integral over A times X dp. So again, this is another important equality. And similarly, we have it for the complement, the integral over A complement of this conditional expectation of X given A complement dp is equal to the integral of A complement over A complement of X dp. And remember, important, this is in fact, the conditional expectation X given A, we better write it as the conditional expectation of X given this sigma algebra. And the same for complement, this is indeed the same. All right, I hope this gives a bit more insight in the conditional expectation. So this leads us to the general definition of the conditional expectation. Let omega fp be a probability space and G be contained in F, a sub-sigma algebra, and let X be a random variable on omega that is either non-negative or integrable. So the expectation is well defined. Now the conditional expectation of X given G, which we denote by this expectation X given G here, is a random variable satisfying the following properties. First of all, measurability. The conditional expectation of X given G is G measurable. And secondly, partial averaging. The expectation of the indicator function times the expected value of X given G is equal to the expected value of the indicator of A times X for all A in G. These are basically the two properties that we have discussed in quite some detail in the previous slides. And this last one, of course, can be written out as follows here. The integral over omega of the indicator A times the expectation of X given G little omega dp little omega, that is by definition the integral over A of the conditional expectation E X given G dp, and that is the integral of A over A times X dp, and that is the indicator function. Then again, we take it back in the under the integral, the indicator function of A times X dp, and that is by definition the expected value of the indicator of A times X. In particularly note that omega, the whole space, is contained in G. So we can also find that the expectation of the expected value of X given G is in this case the expected value of the indicator of omega, which is the whole set, times the conditional expectation of X given G. That is the indicator of G times X. That is the definition of the expectation. Yeah, and moreover, if calligraph G is the sigma algebra of Y, being the fact that Y in B, where B is Borel, for some random variable, then we sometimes write that the conditional expectation of X given G, make it a calligraph G, is equal to the conditional expectation of X given Y. So X given G can be regarded as an estimate of X if the information in G is given. This estimate is completely determined by the information in G, and it has the same expectation as X, and also the expected value of the indicator function over A times X is equal to the expected value of the indicator of A times the conditional expectation of X given G for all A in G. So this brings us to Theorem 2.3.2, and Theorem 2.3.2 gives us some properties of the conditional expectation, and some of these properties will be proven. So let omega fp be a probability space and G again be a sub-sigma algebra of F. Then we have the following properties. I will first do the properties and then I will discuss two. First of all, we have the linearity property. The expected value of ax plus by, a and b in R, is equal to a times the conditional expectation of x given g plus b times the conditional expectation of y given g. The second one, the second property, is known as take out what you know, and that is the following. If x is g measurable, meaning, in fact, and that's also important to know, meaning this, that the expected value of x given g is equal to x, then in that case, then the expectation of x times y given g is equal to x expected value of y given g. That is take out what you know. The proof will come. And here is property number 3, iterated conditioning. Suppose we have H contained in G contained in F subsigma algebras, and X an integrable random variable. Then the expected value of the conditional expectation of X given G given H, that is in fact the expected value of X given H. Fourth property is over here. That is the conditional Jensen's inequality. If function phi is convex, then it is known that we can prove that the conditional expectation of phi of x given g is larger or equal to phi of the conditional expectation of x given g. And finally, fifth is independence. If x is integrable and independent of g, that means that when the sigma algebra of x and g are independent, then the conditional expectation of x given g is equal to the expected value of x, which is constant. All right, we go back some steps. We go back to the first one, linearity. Well, how do we prove these type of things? Well, we prove this, of course, by looking at the two properties, the two defining properties from here, measurability and partial averaging. We look at these two defining properties and see if they hold. Well, first of all, if we look at the expected value of ax plus by given g, we need to verify that the right-hand side, a times the conditional expectation of x given g plus b times the conditional expectation of y given g satisfies these two conditions of the definition of general conditional expectations. Well, by definition, of course, the expected value of x given g and the expected value of y given g, they are g measurable, and so is the linear combination. So the first property is the first is satisfied, right? Now let's look at partial averaging. Let A be in G, and let's write this second one out, the partial averaging. So the expected value of the indicator function of A times this linear right-hand side, the A times the conditional probability of x given g, plus B times the conditional probability of y given g. If we write it out, A and B are constants, so they can be taken out. Furthermore, the expectation is a linear operator, so we can write this as little a times the conditional expectation of the indicator of A times this conditional expectation of x given g, plus B times this expectation of the indicator A times the conditional expectation of Y given G. Now, partial averaging holds for this term, of course, for E of X given G and for E of Y given G. So we can rewrite that as this first part we can rewrite as the expectation of the indicator function of A times X. And that second part here we can rewrite as the expected value of the indicator function of A times Y, ending up with little a times this first expression plus b times this second expression. That is partial averaging for just from the definition. Now we can bring back the little a and the little b in the expectation operator, and we can combine the two. So that is the expected value of little a times the indicator times x plus little b times the indicator times y. And that is indeed the definition. And we can take the indicator function out of the brackets. So that is the expected value of the indicator function of a times, in brackets, little a times x plus b times y. And hence, what we have seen is that a times this conditional expectation plus b times this conditional expectation is in fact the expected value of the linear combination. So one has been proven. Two, again, take out what you know. So when x is measurable, so when x is measurable, that implies this, then the expected value of x times y given g is x times the expected value of y given g. Take out what you know. How do we prove this? Well, a similar way, right? We have to show that the right-hand side of this equation satisfies the properties 1 and 2 of the general conditional expectations. Well, clearly, first of all, clearly x times this conditional expectation is g measurable because it's a product of two g measurable functions. Yes. So now the second one, let A be an event in calligraph G, then what we want to show is the integral of A over A of x times this conditional expectation of y given G dp, that is equal to the integral over A of x times y dp. And this we do again with the standard argument. We have seen the standard argument in lecture number 1. We have indicated the use of the standard argument also in lecture number 2, where it is written out in detail in the book. And here we do it in some more detail. Basically, the standard argument, as you recall, maybe consists of 4 steps. First, we look at the statement for the indicator function. Then, secondly, we look at so-called simple functions, and simple functions are linear combinations of indicator functions. The third step is we look at non-negative random variables, and that is basically an argument where we take a sequence xn, a sequence, and n goes to infinity, a sequence of simple functions, which for n to infinity converges to a non-negative random variable. And as the fourth step, we look at an x plus minus and x minus, and both x plus and x minus are non-negative functions. And by this, we complete the proof. So step 1, again, we look at the indicator function. The indicator function of x, x is the indicator function of b. B is in G, because we want x to be G measurable. Now for any a in G, we would have, we write it out like this. This is the right-hand side, the integral of a over a of x times the conditional expectation of y given G dp. That is, well, replacing x for x we choose first, we choose this indicator function. So we substitute that indicator function is the integral over A of the indicator of B times this conditional expectation dp. And we know, right, that this is also an indicator function of A over omega. Indicator function of A times the indicator function of B is the indicator function of the intersection. And we can write that as the integral over the intersection of A and B times this conditional expectation of y given g dp. Now for this one we know that it is a partial averaging hold, so we can write this as the integral over AB of y dp. And then we take back this indicator function of B, we take it out of the integral range and we take it back in the argument. So it's the integral over A of the indicator function of B times y dp. And well, the indicator of B is x, as we know in this step 1. So this is the integral over A of x times y dp. So we have proven this required relation for partial averaging here. So the result holds for indicator functions. Second step, x, as mentioned, x is then the sum of indicator functions, the sum of I from 1 to n, little a sub I times the indicator function that x is in bi. And bi in G disjoint, so omega is the disjoint, so I should put a dot in here, disjoint set of all the disjoint union of all the bi's. Now again, we can write, this is our right-hand side, the one that we'd like to prove. This is the definition, and now we will substitute our simple function, right? This is the simple function. It's the sum I is 1 to n little ai times the integral of the indicator bi times this conditional expectation dp. So that is the sum I is 1 to n little ai of this expression. Again, we can replace this conditional expectation by y, because that is the defining property of this conditional expectation. Then writing it out, we take the sum inside the integral sign. We replace we interchange sums and integrals. So the integral of a times the sum I is 1 to n little ai times this indicator bi times y dp. And this is now in this step, this is our x. So this is equal to the integral over a of x times y dp. So also step 2 is satisfied. Then step 3, if you recall, we take this non-negative x and we let xn with n running be an increasing sequence of non-negative simple functions where xn converges to x. Then by the monotone convergence theorem, for any a in G, we have that the integral over a of x times this conditional expectation of y given G dp is in limit n to infinity. The integral over a of xn times this conditional expectation dp is, again, now we can use partial averaging for this conditional expectation. So it's limit n to infinity, the integral over a xn times y dp. And then with the convergence n to infinity, xn converging to x, this is equal to the integral over a of x times y dp. And the fourth step here is we write x as x plus minus x minus, two non-negative variables, and we apply step 3 plus the linearity of the conditional expectation. Right? Okay, let me remind you, the third one was iterated conditioning. And we can there prove that the left-hand side satisfies 1 and 2. I have indicated it briefly here, but you can try it yourself if you have time. The conditional Jensen's inequality was number 4, and the independence was number 5. So when X is integrable and independent of G, meaning that the sigma algebra of X and G are independent, then the conditional expectation of X given G is equal to the expected value of X and its constant. And here the proof is that the right-hand side satisfies 1 and 2. Therefore, it's G measurable. And again, we can write it all out and see that also partial averaging is satisfied. Now, I'd like to finish this off with one remark, that the expected value of X given G is an unbiased estimator of X, since the expected value of the conditional expectation is equal to the expected value. All right, we come up with some more definitions that will be shown to be very important and useful in financial mathematics later on. And the first one is the definition of the martingale, and also then of the submartingale and the super martingale. So that's a notion here. Let omega fp be a probability space, and let we have a positive final time, capital T largely equal to 0. So we have a filtration where T runs from 0 to capital T. And we have a random variable xt, again with little t between 0 and capital T. And that is a sequence of random variables adapted to the filtration. So we're dealing with an adapted stochastic process. Now we say that M with little mt with little t between 0 and capital T, that this is a martingale if the conditional expectation of MT given Fs, given the filtration Fs, that is equal to M of S when S is less or equal to T. Yes, so note, of course, note that the expected value of MT is the expected value of MT given Fs, and that is equal to the expectation of Ms. And that is a martingale. So that is the definition of a martingale. The expected value of the process at some time t, given the information up to time s, is equal to the process at time s. And this will be connected to the fairness in financial mathematics. So something like our best estimate of a price process at a future time is the current value of the price process. Secondly, so a submartingale, that is defined as follows, that is MT with little t between 0 and capital T. It is called a submartingale whenever the expected value of MT given Fs is larger or equal to Ms for S less or equal to T. So the tendency rises. Yeah, so it's worth more. The expectation of a process is more than its current value. Yeah, the tendency rises, we call it. And third of all, the super martingale. So I will write this better in the slides when I post them. It's also MT little t between 0 and t, it's a super martingale if the expected value of mt given the information until time s is less or equal ms for s less or equal to t. And that is the tendency false. Yeah, the value of the process is worth less than the value now. Well, let's give an example. Let's give a random, given a random variable and a filtration, calligraphed ft, t positive, then with this we can associate in a natural way a martingale. Namely, xt is the expected value of x given ft. This is an adapted process, as by the definition of xt, and by the iterated conditioning, we have that if s is less or equal to t, then the expected value of xt given the information fs, that is then the conditional expectation of the expected value of x ft given fs. And now we can use iterated conditioning. So that is equal to the conditional expectation of x given fs. And this is a martingale. So this is equal to x of s. So again, we can interpret xt as an unbiased estimator of x given the information at time t. Now, another important definition in financial mathematics is the definition of a Markov process. So you see now we end this part with a couple of definitions and a couple of examples. It is also written in detail in the book on chapter 2, and these concepts and these definitions will come back later in this course. And they fit to the conditional expectation notion. The Markov process is defined as follows. An adaptive process xt, little t between 0 and capital T, adapted to the filtration calligraphed ft, and again little t between 0 and capital T. That is called a Markov process if for all t, and for all s less or equal to little t, which is then less or equal to big T, and s is positive or non-negative, and any Borel function f, there exists a Borel function g in such a way that the conditional expectation of f x t given the filtration fs is equal to g at xs. So this is also interesting. First of all, with the martingales, we didn't have functions. Here we have functions f and g. With the martingales, we just said conditional expectation. And we just said the conditional expectation of xt given fs is xs. So this here is a little bit more general. With the f, we allow ourselves to make functions out of x, like x squared or e to the x. And the answer doesn't need to be xs, but it needs to depend only on xs. And this can be generalized not only to a stochastic process taking values in R, we can also look at random vectors. And f can be a function of more than one variable with more than one random variable. Yeah, so this is an important property because again, although we don't get xs itself, it tells you that up to time s, if you condition, you need a part of your stochastic process up to time t to determine your t value. Yeah, a handy lemma that follows here is to prove that certain process is a Markov process. That is lemma 2.3.4, the independence lemma. So again, the following lemma is sometimes useful for calculating conditional expectations and to prove that a process is Markov. Let omega fp be a probability space, and let G contained in F be a sub-sigma algebra. Now assume we have K measurable random variables, x1, x2 until xk, G measurable random variables, and suppose we have capital L random variables that are independent of G, and we call them y1 until yl. Now let F, just a function F, be a function of R K plus L to R, and it with that as independent variables x1 until xk and y1 until yl, let it be a Borel measurable function. Then we have that the expected value of f x1 to xk, y1 to yl, given G, remember that the x are G measurable, whereas the y's are not, then this is a function G only depending on x, on x1 to xk, where G x1 to xk is defined as the expectation of f x1 to xk, y1 to yl. So if I know G, the elements of G, or if I know in which element of G my outcome lies, then I know the value of x1 to xn, and I have another sequence. Okay? So this is a regular expectation. Yeah? And remember that the expectation is a value. So we finish off with an example of a Markov process. And the example is as follows. Let's flip a fair coin repeatedly. And we say xi, when the event when the ith event is head, xi is 1, and xi is equal to -1 when the ith event is tail. Now we define a stochastic process, Mn, as the accumulation of the values. It's the sum I is 1 to n of x sub I. And now notice that Fn, the filtration after n coin tosses is the information of the first n flips. And remember that M0 is 0, so we haven't started. It's the accumulative value of the coin tosses with either 1 or -1 being added. Now Mn, for n, 0, 1, etc., this is a Markov process with respect to the filtration Fn, n, 0, 1, etc. You can see it as follows, Mn plus 1, so the accumulation after n plus 1 coin tosses, that is equal to the accumulation after n coin tosses, Mn, plus xn plus 1, plus the n plus first coin toss, where Mn is, of course, Fn measurable, and that new coin toss, xn plus 1, is independent of Fn. Then we have the following, so like we have it in the independence lemma and the Markov process, then the expected value of a function of Mn plus 1, given the filtration of, at the nth coin toss, that is equal to, we write this expression Mn plus 1, we write it out. So it's a function of Mn plus xn plus 1, the n plus first coin toss, given the information Fn. And then a Markov process and the independence lemma tell us that this is equal to a function g of Mn. And now this function g of m is the expected value of f of m plus xn plus 1. And the expected value of this expression with the independence of xn plus 1, the independence of that from mn, this is equal to the value of f at m plus 1 times 1/2 plus the value of f m minus 1, so that's the tail, then we subtract 1, f m minus 1 times 1/2. So that is the definition of that g, the expectation of this operator, of this expression. So in total, the expected value of f at m n plus 1, given the filtration at n, is f of mn plus 1 plus f of mn minus 1 over 2. And as this expression only depends on mn, it is hence a Markov process. So this concludes today's lecture. Thank you for listening. I have listed the exercises that we will do. Coming Friday, the exercises are 2.1, 2.2, 2.4, 2.5, and 2.6. Next Wednesday is May 5th, so we will not have class. And next Friday, we will then do 2.7, 2.8, 2.9, 2.10, and 2.11. Thank you for listening, and I hope to see you attending next time.